Hi, everyone. In this video, we're going to talk about natural units. Now, natural units can mean sort of different things depending on what field you're talking about. So in particular, in this video, I'm going to focus on natural units as they're often used by particle physicists. Now, in general, why would we use these natural units? Well, it's really to make your life easier. So depending on what field you're working in, which field of physics that is, different constants of nature are going to show up in your equations, and which constants often show up depending on what particular field you're working in. For instance, if you're working in a field involving gravitation, then Newton's constant is going to show up in a lot of your equations. And this makes the equations a little more complicated. And so one thing you could do is to choose to work in a unit system such that those constants are set to 1. Right? You can always choose whatever units you want to work in. And so why not choose a unit system that makes our constants of nature some really nice number, and 1 is a particularly nice number. Now, in particle physics, usually, since we're talking about little tiny particles, usually gravity isn't very important. On the other hand, our particles are often moving quite quickly. And so c, the speed of light, comes up often. So this is c appears in a bunch of the equations in particle physics. These are, when we're thinking about particle physics, since the particles are moving so fast, this is a special relativistic theory. And so factors of the speed of light come up all over the place. And so it'd be nice if we could get rid of all of these factors of the speed of light. The other constant of nature that comes up a lot is Planck's constant, because particles are, of course, very small, and so they're going to behave in a way that's very quantum mechanical. And so we think of Planck's constant as the constant of nature that governs quantum mechanics, or the scale of quantum mechanics. And so similarly, we can work in a unit system where we set h bar equal to 1. And so that's how natural units are generally presented, is we're saying c equals h bar equals 1 in the case of particle physics. And in fact, actually, this is under constraining the problem. You actually are free to choose 3 constants of nature and set them all equal to 1. Now, if you do that, you've sort of completely constrained the problem, and then you are forced into a particular unit system with those choices. In particle physics, there's not really a third constant of nature that is so ubiquitous that it makes sense to do that. So instead, what we'll do is we'll use our remaining freedom to pick a unit of energy, which is a unit of energy which is just convenient for the scale of the problems that we're often dealing with in particle physics. So depending on who you talk to, this is going to be electron volts or MeV or GeV, some form of electron volts. In this video, we're going to specifically focus on setting our energy scale with GeV. So our third choice will be GeV. So in this video, I'm going to actually present thinking about natural units in a slightly different way than people often do. So as I said, people often think about this as a choice where we are choosing a particular unit system such that, in this case, c and h bar happen to be 1 in that particular unit system. I'm going to think about it in a slightly different way, which I think is consistent with what you mathematically end up doing in particle physics a lot, and I think it makes a lot more sense. Also, this is for students who are new to natural units, they're pretty challenging to sort of wrap your head around, and I think this other way of thinking about natural units is a little more digestible. And so rather than thinking about these as a set of units, or as really constraining the set of units that we're using, we're going to really think about it as a definition of a new set of variables that we're going to use in our equations. You can also think about it the other way, and mathematically this is equivalent. But I sort of prefer this other way of of thinking about it. And so, as I mentioned, we're going to want C and H bar to sort of equal 1, or we want to get rid of them in our equations. In a way, this other way of thinking about it, we aren't necessarily setting them equal to 1. We're just going to redefine our variables in a way that absorbs them into the variables. And then the third choice we're going to use is going to be about energy. So let's start by thinking about energy, because it's going to be, we aren't going to really be doing anything weird with energy. All we're going to choose is we're going to choose a particular unit for energy that's useful in particle physics. So we will choose to measure energy in GeV. And in case you're more used to working in SI units, which is joules, it'll be useful to recall that 1 GeV is equal to 1.602 times 10 to the negative 10 joules. Again, this is just a standard unit convention here. I'm actually not doing anything new. I'm just saying we're going to work in GeV, and joules, which you might be more familiar, are related to GeV like this. And we'll need this. Okay, so the next thing, another variable, right, that we might be very interested in particle physics is measuring the mass of our particles or other things. And so we want to think about a different way of measuring mass, or a different variable for mass, such that we can measure the mass as some power of GeV. At the end of the day, we want all of our variables to be expressed as some power of energy, which is to say some power of GeV. So we want to redefine, or maybe not redefine, just define, really, a new variable proportional to mass that has units which are some GeV to some power. And this is really what we're going to, this statement that I'm making here is what we're going to try to do for all of our variables. We're going to try to define a new set of variables so that all of them can be measured in some power of GeV. And what we'll see is this is sort of going to be equivalent to setting C and H bar equal to 1 in all of our equations if we do it the right way. So before I tell you what this new variable is, let's gain some intuition for this. So recall, these are relativistic theories. So an equation that comes up a lot is E squared equals m squared c to the 4th plus p squared c squared, right? This is E equals mc squared, but it's actually the more accurate form where we're including the energy, kinetic energy, right? Energy due to momentum. So this is rest mass plus kinetic energy is the total energy. So what this equation is. And wouldn't this equation look so much nicer if the C's weren't in it? And so with that in mind, we're going to define what I'm going to call the natural mass. I don't know if anyone else uses that term. I might just be making it up, or maybe someone else uses it. I'm going to write it for now as m sub n, although since ultimately we'll be measuring all of our variables in terms of their sort of natural analogs or natural versions, whatever you want to call it. Ultimately, I will drop this, but for now, let's keep it there. M sub n is going to be defined as mc squared. So again, this is natural mass. And the m on the right-hand side of this equation is sort of the normal mass. which you might measure in kilograms if you're working in SI units. So I'm going to define this new thing. And notice that if I always work, like if I'm doing experiments or something and I'm writing some data down, I'm measuring some masses. If when I write it down, I always multiply that mass by c squared, I'm not losing any information by doing this. So if I keep track of this variable, which I'm calling the natural mass, instead of the old-fashioned mass, there's literally no loss of information because they're just proportional to each other. So if we just all agree that when I write the mass, I'm always multiplying it by c squared, there's really nothing wrong with that. Furthermore, we aren't going to want to measure, well, I guess actually before I say that, notice this is something which is mass times speed squared. So if you remember your kinetic energy, which is 1/2 mv squared, units of energy are mass times a speed squared. And so this has units of energy, so that's good. I mean, I guess I knew that because that's E equals mc squared. So of course it has units of energy. It will be useful just so you have it in your back pocket if you're working with natural units to actually plug in these constants and see if I give you a mass in SI units, so in kilograms, what would be sort of the conversion factor? What do we multiply it by to get out our natural mass in GeV? So we can do that. So Mn is equal to the good old-fashioned mass, which I'm imagining I'm measuring in kilograms, multiplied by the speed of light squared, 3 times 10 to the 8 meters per second squared. Now, if I just multiplied these things through, that would give me the natural mass in joules. So that's kind of good, but instead, like I said, in particle physics, we often want to work in GeV. So now we're just going to do a normal unit conversion to this and say 1 GeV is 1.602 times 10 to the negative 10 joules. And if I plug all of these numbers into a calculator, what I'm left with is 5.6 times 10 to the 26th. This is some number. And if I multiply that by the mass in kilograms, then that gives me the natural mass in GeV. So we can write this sort of conversion factor where this is the mass in kilograms. So if I give you the mass in kilograms and I say, what is the natural mass in GeV? You multiply that mass in kilograms by 5.6 times 10 to the 26, and that gives us the mass in GeV. And again, this is just they're proportional. So, so I've lost no information in recording this mass in GeV instead of in kilograms. Okay, so let's do the same thing, but for momentum. So I'm going to define the natural momentum. Again, I don't know if anyone else uses that term. I'm just using it, which I'll call P sub n. And this is just going to be equal to the normal momentum times the speed of light. And again, we want to ultimately measure this thing in GeV. If I just multiply momentum times the speed of light in SI units, I would get something out in joules. So we want to instead say, oh, if my pen wants to work. Oh no, did my pen just die? Oh, shoot. Oh, there it goes. Okay, good. All right. So this is equal to our momentum, whatever it is. I want to leave that as a variable, times 3 times 10 to the 8 meters per second. If I give you the momentum in kilogram meters per second and multiply it by speed of light in meters per second, that gives us joules. So we want to instead, again, multiply this by 1 GeV divided by 1.602 times 10 to the negative 10 joules. And if you plug all those numbers into your calculator, we're left with our natural momentum as measured in GeV is going to be equal to 1.87 times 10 to the 18 times our momentum measured in kilogram meters per second. So this is measured in GeV, and this is measured in kilogram meters per second. So I can define this new quantity, which has units of GeV, by just multiplying the good old-fashioned momentum in SI units by this number here. And again, it's just a proportionality factor in some senses, and so I lose no information by doing that. I'd also like to sort of take a step back at this time. So what we're finding is we can measure mass and momentum both as energies. And in a way, that's getting at something sort of deep in relativistic theories, which is that we sort of want to treat energy, mass, and momentum on equal footing. So the fact that we can measure them with the same units suggests this sort of underlying physics, which is that we want to sort of treat them in the same way. I'll also note that equation that I had earlier, which is E squared equals m squared c to the fourth plus p squared c squared. If I rewrite this equation in natural units, I mean, E sub n, again, energy, we aren't really measuring differently. It's just an energy, but we could call it E sub n and just say it's equal to the normal energy. This is equal to the natural mass squared plus the natural momentum squared. And so this is the sense in which by rewriting our equations in terms of these new variables, it's like we're setting C equals to 1, right? This equation looks the same as the last one. And what we'll usually do, again, I'm writing the sub n for the purposes of this video, but in real life, no one ever does that. They just say E squared equals m squared plus p squared. And we just say this is the equation in natural units. But really what we're doing is we're measuring these sort of equivalent masses and momenta, which are measured in GeV. And then the units of this equation and the dimensions and everything sort of makes sense. And so we're seeing that by defining these natural quantities, our equations are becoming simpler. And we see it explicitly in this example, but this is gonna remove all the speeds of light from all of our equations. So that's where I'm saying this is really the same thing as just setting C equal to 1 in some senses. Okay, so when you're doing physics, some things you want to measure: energy, mass, momentum, great. The next thing you might care about is time. Right, this is a standard thing that we can measure. And we want to measure this again as a power of GeV. So sort of energy to some power. So how can we do this? One thing we can note, so far we've been talking a lot about the speed of light. We haven't been talking about Planck's constant at all, which is the other constant that we're going to set to 1. So recall that h bar has units which can be expressed as joule times seconds, or I guess more generally, energy times time. So this is starting to suggest that if we somehow define a new variable of time, where instead of using the speed of light, we use Planck's constant, then we can imagine those units of time canceling out and being left with something which is a power of energy. And indeed, that's what we'll do. So we'll define a natural time, T sub n, as the good old-fashioned time. We want our units of energy, or sorry, our units of time to cancel out. So we're going to divide this by Planck's constant. Because the units of seconds, if you're working in SI units, will go away, and we'll actually be left with inverse energy. So inverse GeV as our units, and that's okay because that's still some power of GeV. So if we do this again, so if I take T and then I plug in what H bar is, this is 1.055 times 10 to the negative 34 joule seconds. If I just plug this in, I'm going to get an answer for my natural time in units of inverse joules, which we could do. But again, in particle physics, a joule is just not a very useful unit of energy. So instead, now we're going to do the unit conversion and use the fact that, again, 1.602 times 10 to the negative 10 joules is equal to 1 GeV. So we see our joules cancel. The seconds that are left here are going to cancel with our normal time variable, which I'm imagining we're measuring in seconds. And so if you plug this into your calculator, we're left with our natural time being 1.5 times 10 to the 24 times the time measured in seconds. So here we would plug in T in seconds, and then we'd get out our sort of natural time, which is in inverse GeV. Now, I said previously when we were thinking about mass and momentum that the way things worked out, the fact that we were measuring them in terms of just GeV, that they seemed straight up like an energy, that made sense. It turns out this also makes sense, that time is sort of like an inverse energy. And one way to think about that is if we think about wave mechanics, a frequency, high frequency, is associated with high energy. So we would think frequency could be measured in energy because they're sort of high frequency, they're proportional to each other. Time, which is like period, that's inverse frequency. So again, we're seeing that sort of this, so I mean, that's to say that big period is small energy, right? It's not usually the way we think about it because we think in terms of frequencies, but it's equivalent. Big period, so big time, is small energy. So again, it makes sense physically that time is something that's sort of like an inverse energy. So it makes sense that our units for natural time end up being an inverse energy. Okay, and then the last variable that we'll touch on is length. We're going to define our natural length as x sub n equals x divided by ch bar, where I'm imagining, again, measuring x in meters and just normal SI units. So this is x divided by 3 times 10 to the 8 times 1.055 times 10 to the negative 34 joule seconds. Sorry, I'm writing things backwards, and I also forgot my meters per second over here. So this would leave me with something. So notice my seconds cancel. My meters will cancel with my x, which is up top. And so we'd be left with something inverse joules. Again, we want to work in GeV. So doing the unit conversion, this is times 1.602 times 10 to the negative 10 joules divided by 1 GeV. So now our joules cancel. And again, our meters are going to cancel because X will be measured in meters. So then our sort of natural length variable, which I'm defining, can be computed by multiplying 5.1 times 10 to the 15 times our position or our length as measured in meters. And notice, just like with time, what we're left with is inverse GeV. Again, that makes sense. And there's two ways we can think about this. One is that we're in a relativistic theory. So we really want to treat space and time on equal footing. So it's kind of nice that the units we have for distance match the units we have for time. They're both inverse energy. The other way that it makes sense is, again, if we think about wave mechanics, then a short wavelength, so short length, should be related with high energy. So again, we're seeing from wave mechanics that it makes sense for there to be this inverse relationship between these two. Okay, so to summarize, this is a nice way of thinking about natural units. It's mathematically equivalent to any other way you might think about natural units. At the end of the day, we have these different boxed equations, which let's see if we can see. Oh, that didn't really help that much, which are relating time and position and momentum and mass. We're relating how one would measure them in SI units to how one would measure them in natural units. And so I would recommend keeping all these numbers with you so that you don't have to reinvent the wheel every time. And instead, what you can do is if someone hands you the mass and says, hey, convert this to natural units for me. And if they gave you that mass in kilograms, you just know to multiply it by 5.6 times 10 to the 26. If they gave you the mass in grams instead of kilograms or something else, of course, you would just first do a normal unit conversion to kilograms and then multiply it by this number. And that's going to give you the mass in natural units as measured in GeV. And again, at the end of the day, I've written all of these quantities with this sub n subscript. No one really does that. They just declare we're working in natural units. So you know all of your variables. You could imagine secretly have that sub n subscript. And what that's going to do for us is it's going to get rid of all of our speeds of lights and our Planck's constants. H bar is what I mean by that. So some people refer to that as a reduced Planck's constant, but whatever, H bar, right? These are all set to 1 in our equation. So we don't need to keep track of them anymore. And then at the end of the day, you can restore the constants of nature into your equations if you want to, either by doing dimensional analysis or by going back to these sort of definitions I have here of natural mass, and then replacing all of the natural variables back with the irregular variables, right? So you would say, oh, our regular mass is the natural mass divided by the speed of light squared. And so if everywhere in your formulas, actually, sorry, you don't need to do that. Just everywhere in your formulas, you replace the mass with mc squared. Sorry, that was unnecessary to solve that equation. Okay, so that is the way I like to think about natural units, as really a redefinition of our variables to these new natural variables, which are proportional to all of our old ones And so again, the thing I really want to stress here is we are losing zero information by doing this. Literally zero information, because keeping track of writing down MC squared every time, you know, which by that I mean you measure mass and then you multiply it by C squared, and that's what you record in your notebook to keep track of mass. That is no different than keeping track of mass in kilograms. And so that's why natural units are so handy and we don't lose anything by using them. All right, so that's natural units.